Our next speaker is Pratap Vishnoi, and he's from the New Chemistry Unit and International Center of Material Science at the Jawaharlal Nehru Center for Advanced Scientific Research, JNCSR, in Bangalore. He's going to tell us today about recent developments in magnetic halide perovskites of heavy transition metals. Thank you very much, Pratap.
Yeah, thank you, Professor Driscoll, for the introduction. And thank you, Tony and Natalie, for the invitation to speak in this meeting. So my name is Pratap Vishnoi, and I'm faculty at the Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. And I also take this opportunity to thank Professor Rao for his enormous support in research that we do. So we had two excellent talks on halide perovskite largely based on lead iodide perovskite and their optoelectronic properties. So if you look at this area has flourished in the last 15 years, largely because of the photovoltaic applications. If you look at recent past, last 5 to 10 years, there is an expansion of the chemical spectrum of these halide perovskites, meaning people are discovering perovskite, which are metals which are not lead, expanding the chemical horizon, and the type of structure that are being discovered, and also properties thereof. So when I joined my second postdoc, moved from Bangalore to UC Santa Barbara about 4.5 years ago, to work in Tony Chitam's group and Ram Seshadri, I was told that why don't we work on metal which are from transition metal group and look at the structure type that comes out and also the properties, typically magnetism and beyond. So we picked ruthenium there. I'll tell you why we picked ruthenium, and then we discovered several materials and then moved on. So here today I'll be covering ruthenium-based halide perovskites as well as molybdenum-based halide perovskite. Ruthenium basically has 1 unpaired electron, and molybdenum has 3 unpaired electrons. And I'll be talking about largely their magnetic properties and the perovskite types. There's new composition and the structure types that we discovered. So I don't think I have to explain the basics of the basic structure of the halide perovskite, which is very beautifully laid out by Professor D.D. Sharma just now. So, but to put in context and relate this to the double perovskite, I'll be largely talking about double perovskite. So let me connect this monoperovskite, monoperovskite with double perovskite. This metal, as just mentioned, is a perovskite is basically a BX3 type of composition with crystalline nature, where A is a cation, which is a fairly large cation, which typically in all inorganic cesium and hybrid is methyl ammonium cation. And then metal we have typically which is 2+, and most system it is less 2+, and in some cases there are 10 2+, and then halides we can choose at will. So when these metal and halide combine together, they form a octahedral coordination, and then the corners of this octahedra connect in all the directions, all the 3 axes, to form a 3D lattice, which is basically negatively charged, and also it has a large cavity called A-site cavity. Now this cation can easily go and sit in the cavity and form a stable lattice. So the material, this material, as I mentioned, has flourished over last 15 years. One of the reasons is the optoelectronic properties, but there's another reason behind this is because they're very easy to make. With some amount of experience in synthesis, one can make them easily using solution processes and in various forms like powder, thin film, and flexible devices by coating on flexible substrate. And by doing this, one can tune the light absorption the efficiency. And from there, the tunable the properties are can be tuned. So, and there are some of the ways, but then because there is a large interest, and as I mentioned, the various chemical compositions have been discovered, and they are by one or the other way relates to this typical perovskite which I was talking about. So some of them are double perovskite, where we use 2 types of metals or a metal and vacancy in the perovskite sublattice, and then one can reduce the dimensionality to 2-dimensional. There could be, this is 1, 1, 1, or 1000 type of 2D perovskite. And that can be further reduced to one-dimensional lattice. So in my talk, as I move forward, I'll be largely focusing on the double perovskite, which is, most of them are one-dimensional or two-dimensional, and some of them will be three-dimensional. So moving forward, as I mentioned, we discussed why don't we work on ruthenium trichloride, and what was the motivation to work on ruthenium chloride. Ruthenium chloride, one of the compound that exists in the literature is ruthenium trichloride, which has two polymorphs. One of them is a linear chain formed by phase sharing. Other one is the lead 2D materials, pretty similar to molybdenum disulfide, which is the van der Waals 2D system. And each layer of this contains ruthenium. These are red balls, and this light color, these are the chloride ligands. Now, if one looks at the only ruthenium atoms, they form hexagon lattice, exactly similar to the carbon arranges in graphene sheet. And since, as I mentioned here, the ruthenium has a high spin orbit coupling strength, because this element belongs to 4D series, which because of the heavy nucleus, it has a significant influence on electron spin. So this particular entanglement we call SOC, and due to which this system is the J effective half. And this is one of the criteria for selecting a quantum spin liquid material. So the atom should have a spin half system. And then when this system, here is the electronic configuration. The ruthenium has T2Z and EZ orbital in octahedral setting, which basically is split because of the 6 ligands chloride around, and the ruthenium is always, no matter what the ligand is, going to be low spin because of the heavy metal. And we have one unpaired spin, which further splits because of SOC, and we have J effective half system. And when these atoms are in the hexagonal setting, we have some sort of this type of magnetic, expected to be this kind of magnetic correlation, and which is basically the spin quantum liquid behavior. However, there's a lot of interest in this material, but there is still, this phase is not found in RuCl3. It's typically order magnetic, antiferromagnetically at very low temperature. So a lot of work is ongoing in this area. But what we thought of is, because there are only few compounds with ruthenium halide is known. One of them is this. So why don't we put ruthenium-3 in a perovskite lattice? And that's where the double perovskite comes in picture. Because ruthenium-3+ here is a 3+ charge, we cannot simply replace the 2+ metal, which is in ABX3, with ruthenium-3+. So there's another lattice, another type of perovskite exists, is double perovskite, where it's very simple to understand, where in this we have the B site, which is splitted into two sites. One of them will accommodate 1+ metal, and other one will with 3+ metal. And that's where we can accommodate ruthenium. And to maintain the charge balance, we can choose another metal, which is 1+. Typically, in most cases, people choose silver 1+, or sodium, as just now Robert mentioned. So here, this type of lattice becomes stable largely because of the ordering led by difference in charges. One is 3+, and one is 1+, and the other one is 3+. So there is a difference of 2 electrons here, difference by 2+ here. So, and then, and of course, historically, this type of structures are known slightly before the single perovskite, about a decade before. That was known since 1993. And this is 1983. And it's also, in early literature, this perovskite was called as alpha-azolite, and still it is called so. So here is the diagram how it shows the splitting. The monoperovskite, we split the 2+ metal site into 1+ and 3+, and choose the composition that you want to put in lattice. So in this, ruthenium-3 should be possible to put. And we started to work on hybrid system, choosing methylammonium as the cation to go in the cavity. So we carried out this reaction, and we found this composition, as there by the elemental characterization and the beautiful hexagonal crystal, of course. But the structure of that crystal suggested it's not a 3D perovskite. It's rather a 1D chain, which is formed because of phase sharing of the octahedra, where the opposite octahedra of each of these faces of each of these octahedra actually phase share in one dimension is typically the C axis, and in this compound is silver and ruthenium, which actually order alternatingly in the chain, and this the cation 1 plus methylammonium that sits in the interchain gap and form strong hydrogen bonds with the chain to make the lattice stable. And this was happened to be the very first report on halide double perovskite, hybrid halide double perovskite, where both the metals were from transmetal category. So this was kind of surprise. We didn't know why this is forming 1D, where there's a hybrid double perovskite were existing before. So then when we went on to change the chemical composition, and let's see what happens instead of sodium, instead of silver, if we use sodium, which is another 1 plus metal, or potassium, to see what happens when we change the size. So what we obtained in all these three compositions is the same structure type. And not only that, even if we change chloride with bromide, still structure type is the same. It's a one-dimensional hexagonal lattice. So because there are about half a dozen structures which are forming one-dimensional structure, we thought of looking at in more details in terms of certain parameters, called tolerance factor and radius ratio. And these are mathematical parameters which basically one can work around and say that whether the compound is going to be perovskite or not. So here we had about a 6 structure, which is one-dimensional perovskite lattice, and there are about same number of structures existing before, which are actually corner-connected 3D structure reported by Tony's group earlier in various different papers. So here we calculated these two parameters using the radii of the constituent ions for the one-dimensional structure and also the earlier non-3D structure, and to see what happens. And here are the output of the calculation. So these are the compounds which are one-dimensional. We see that the tolerance factor of these compounds are slightly more than 1, not too high. And the radius ratio, which is less than 0.41. 0.41 is nothing but root 2 minus 1, which is the condition for system to form 6 coordination geometry. So we see these parameters, which are kind of off to form 6 coordination geometry. And then we looked at the other bunch of compounds where we see tolerance factor is in the perovskite range, which is validated range for the perovskites. For the ABX3, it is well known. It's also known for double perovskite that when one expects to form a perovskite, the tolerance factor should be within 0.8 to 1. And we see it's well within that range. And also the radius ratio is above 0.41. So all these 3D perovskites, when we plot in this radius ratio versus tolerance factor, the map, they occupy this corner, which is high radius ratio and low tolerance factor. Whereas the 1D perovskite occupying corner here, which is high tolerance factor and low radius ratio. So here we kind of, with all the known structure, we thought this could be the reason why our compounds are forming one-dimensional structure. And then we looked at to see whether this model, what we designed here, work for the known inorganic compounds. And there are about, at that time, about 3 years ago, close to 140 all inorganic compounds were known, where the A cation is cesium instead of methylammonium. And what we see is our model, which we designed based on these two parameters, actually predict most of these structures, and that accuracy is close to 90%. That means the message here is using these two combination of tolerance factor and the radius ratio, one can even predict a compound which is not discovered before and can say whether it's going to be 1D or it is going to be 3D. Sorry. One of the things which you notice here, as we increase the 1 plus cation size, the tolerance factor becoming more appropriate for a 3D structure. And what happens here is, this is the only case where we get a mixture of compound, 1D and plus a 3 to 9 phase. This indicates that when one of the parameter out of 2 is appropriate for 3D structure, the chances are high that compound is trying to form a 3D structure, which is becoming more favorable over a 1D structure. But however, many times when we try to form a 3D perovskite, this 3 to 9 phase becomes more favorable over 3D structure. And that's the reason we are getting a mixture of 2 phases. Now, to mention here, and the interesting fact is the 3-2 phase contains ruthenium, diruthenium, Ru2Br9 dimer with a very short Ru distance, which is about 2.8 angstrom. This also means there is a ruthenium-ruthenium interaction. And as I mentioned, ruthenium that we are using, Ru3 plus, has 1 unpaired spin. So when 2 ruthenium centers come closer with a short distance, the chances that they might interact antiferromagnetically within the dimer and can quench the magnetic moment. And we exactly see that in this form, the magnetic moment is nearly quenched to, nearly diamagnetic. Whereas the earlier report on iron, which has about 3.6 angstrom distance between 2 iron, doesn't show any quenching of magnetic moment. The magnetic moment obtained from the experiment is close to the theoretical moment based on spin-only formula. That means the 2 iron centers in the dimer, they are not magnetically interacting antiferromagnetically. Well, so then we also looked at the magnetic data of the 1D structure, one of these 6 1D structure. What we see is the system interact antiferromagnetically. And this is the sodium-based system where we see the Curie-wise theta is about minus 14 point K. This is weakly antiferromagnetic system, as is likely to be along this chain. And then we analyze this data. So one of the motivation to start this work was to find out what is the spin-orbit coupling strength in the ruthenium when you put ruthenium metal in different type of lattices. So here, the data can be fitted to a model called Kotani model, which has a component called spin-orbit coupling strength. By fitting data, we can extract the value. We see a slightly poor fit because the system is interacting antiferromagnetically. And let me mention that this Kotani equation is designed for the system which has a metal complex, the magnetic metal in 6 coordination, perfect octahedral, and that don't interact. So non-interacting magnetic system is the primary criteria for this. So deviation that we see is because of primarily because this antiferromagnetic coupling. But however, we can have approximate value of spin orbit coupling strength that is about 600 inverse wave number. So moving forward, the model that we design is, I'll be talking about some more structures based on that, whether you're going to get 1D or you're going to get 3D. One of the papers that about a year and a half, it came out from Pat Woodward Grove, which suggests that if you calculate these parameters for a composition, here it is rhodium-based system, which is the right side neighbor of the ruthenium. It's a non-magnetic, of course, because of the d6 electrons, which are paired. But its tolerance factor and the radius ratio is perfect for the 1D structure that we laid out. And all these 4 compounds are actually one-dimensional structure, similar to what we obtained for ruthenium. So that further validates our model on the 1D system. So while doing this, as I mentioned, we looked at about 150 structures in various crystallographic database. And then we segregated the structure for other reason based on halides. So what we found is the majority of the structure were fluoride-based durable perovskite, and then the number drops. And by the time we are at iodide, there's no compound known. So that's then we wrote this why iodide perovskites are so rare. So here I also want to mention that the methylammonium lead iodide is a monoperovskite with so much interest, and this has a narrow band gap. But as Professor D.D. Sharma mentioned, that the instability and there are a lot of issues in that, and people are looking at other alternatives, including low-dimensional 2D system and so on. But one of the alternatives that people are looking is the double perovskite iodide. And there's a massive interest, amount of interest in that. However, there was no iodide perovskite known. So it is important that, to boost the discoveries in this area, whether we can give another model which can tell why it is absent, despite the fact that there's a lot of interest in that. So we came up after this database search with a couple of criteria. So if we look at the tolerance factor and the radius ratio. So if particularly the radius ratio, for a fluoride compound, we need metal which is 0.9 angstrom or above. And in periodic table, there are not many metals which can fulfill this criteria. Of course, bismuth can do it, but then bismuth has other problem. Whenever we try to make it, there is a more stable phase, which is, let's say, if you are making methylammonium-based bismuth double perovskite, the end product is often methylammonium 3, bismuth 2, I9. So if somehow one can manage to suppress this phase over a double perovskite, then it is possible to make with bismuth as well. But however, it's not been achieved even by far. Based on this, the calculation, we also predicted close to 300 structures, including metal which has a radius, the radius of 0.9 angstrom or above. And today, iodide perovskites are still rare, but they're not unknown anymore. About a year ago, last year, we reported 5 new structures that I'm co-authoring the paper. And these are basically based on F-lock elements. So, and after working on this work, we realized that iodide perovskites even more difficult to make than we were knowing sometime before this paper appeared online. Okay, so, and here again, you see this compound. Has interesting the absorption and emission properties based on metal that are used from F block in the perovskite lattice. And there is a magnetic, of course, weak magnetic exchange interaction, but it does happen at very low temperature. So far I talked about ruthenium, which is a compound based on 1 plus, the ruthenium 3 plus with 1 unpaired electron. Then we recently looked at whether we can make these compounds using the model that we used with molybdenum, which is molybdenum 3, which is with 3 unpaired electrons. And again, our calculation for the methylammonium silver molybdenum chloride 6 suggests that it should be one-dimensional, and indeed we have a structure which suggests clearly it is one-dimensional and is phase pure. We don't see any other phase in this compound. And because these are magnetically diluted system, as the case of ruthenium, which is because they are separated by non-magnetic metal. So we see a magnetic correlation, but it is at very low temperature, about 2.5 Kelvin or so. And then very recently, as Professor D.D. Sharma mentioned, that the properties, particularly the optoelectronic properties of halide perovskite, can be tuned by mixing halides. So here we have an example, a series of examples, where the magnetic properties can be tuned by mixing 2 halides. Here it is the sodium-based compound, sodium molybdenum chloride, the parent compound. In that, we can keep increasing the bromide content and to get mixed halide situation, where the chloride and bromide basically occupying same crystallographic site. So basically, these are same structure type. We don't see a change in structure at bulk level, and of course, this from single crystal is clear that these are in the same phase, but one can increase chloride without a phase segregation, and they're very stable in under ambient condition. Also, the elemental distribution suggests that there is no phase segregation. Phase segregation often is a complex situation. It's create a lot of issues, particularly in double perovskite, because there are more combinations possible, because there are ternary compounds. So, and then also we see, as expected, as we increase the bromide content, unit cell volume increases. But interestingly, we don't know the reason, but the C by A ratio remains constant. It doesn't change. And we also looked at other structure which has one-dimensional structure. There also the C by ratio is similar, which is close to 0.95. So it seems to be constant across the all compositions. So what we looked at here is and the magnetic measurement on the series of compounds. And before that, it is important in molybdenum and any transition metal compound that the oxidation state is carefully analyzed, because the number of unpaired spin with the electron we talk about in transition metal ion depend on oxidation state, and that might significantly impact the analysis of magnetic data. So here we see the molybdenum in these series of compound, and the previous compounds too is in 3+ state. We don't see any impurity of other the oxidation state, and that becomes further clear from Raman spectra, where we see, typically if there is an oxide, one would expect a peak around 800 inverse wave number, and also around 950 inverse wave number. We don't see very tiny peaks, of course, can arise from surface oxidation. And this was clearly analyzed in a recent paper from Tony's group, where it suggests that it's very, very difficult to control oxidation of molybdenum. But that is in 4+, and it goes to higher oxidation state, and hard to control that. But in this structure, the 3+ in one-dimensional setting, we can precisely control this. It does not oxidize to any higher oxidation state, even under ambient condition, for some days. Well, and then we looked at the magnetic data of this series of compound by changing chloride, mixing chloride, bromide in chloride. And we see, it's quite interesting to see this. The magnetic correlation temperature, that is antiferromagnet in all this system, actually increases as we increase the bromide content. And it varies from about 5 Kelvin to about 7 Kelvin, when the bromide content reaches to about, chloride to bromide become 2:4 ratio. Now, it's not very clear the physics behind this. Why? Because it's counterintuitive compared to what is known in the literature. Because with bromide, molybdenum distance in chain increases. That's supposed to reduce probably the magnetic correlation temperature. The magnetic exchange become weaker, but here we see is becoming stronger, which is further verified by heat capacity measurement, where the mixed halide is showing the anomaly in heat capacity at higher temperature. Now, what we know so far is, based on when the MO distance, molybdenum distance is increased, we see the magnetic correlation strength increasing, but we believe this correlation is due to the distortion in the molybdenum octahedron. So with only chloride, we see the octahedra showing highest distortion, which is the bond angle variance we calculate using known formula. And this distortion decreases as you keep on mixing bromide. And probably that is leading to a stronger magnetic exchange interaction. And this was further verified by computational studies in collaboration with Professor Sapanpati's group at JNCSR. Well, and then, of course, we can tune the optoelectron, the optical properties, absorption band shift to show red shifting on mixing the bromide, which I have not brought it here. But now let me switch gears slightly to change a cation. When we had methylammonium in the system, the old compound, I saw the series of compound which are one-dimensional, not only in molybdenum, but also in ruthenium. But the moment you change to cesium, it becomes 3D lattice. So it's a cesium-2 sodium molybdenum chloride 6, a double perovskite with a perfect cubic lattice. And we also checked it's a possibility of phase transition. We don't see this compound is showing any phase transition, at least in the temperature from liquid nitrogen to high temperature. That means it's a very stable lattice. But essentially what I want to highlight here is we have a lattice here in this. If I just consider molybdenum metals and plot make a diagram like this, we see there are tetrahedron with the corner occupied by molybdenum metal, each of which has 3 unpaired electrons. Now, this is one of the structure types which possibly can give quantum spin liquid material, because these ions at the corners of tetrahedron cannot magnetically find a single ground state, particularly when we talk about antiferromagnetic coupling, because they cannot cancel each other. And such situation often leads to the quantum spin liquid, meaning they don't antiferromagnetic couple even at very low temperature. We see, of course, there is an interaction, a magnetic exchange interaction happens around 3.5 Kelvin or so, but we see the Curie-wise temperature, which is quite high here, about 15 or so. So we see a frustration factor close to 5. That means there's some amount of frustration is there in this material, and which probably indicates that such materials could be a promising quantum spin liquid moving forward. But however, there are a lot of work to be done to strengthen the local short-range coupling by strengthening the bond covalency and so on. We are working on that, how to strengthen this the short-range ordering and suppress the long-range ordering to increase the frustration factor. These are further ongoing work. So, and this 3D material, if I compare the band gap with the key double perovskite, which is within the double perovskite, which are optoelectronic, useful for optoelectronics, this is one of the champion material, because as I mentioned, iodide is not known. So the material with the narrowest band gap known is the bromide. So compare with this, we have this material which is slightly narrow band gap, and if you look at the stability, which is very stable for a month or so under ambient condition, considering the fact that we have a metal which is molybdenum 3+, is actually vulnerable to the ambient oxidation. But still, it seems that in these kind of lattices, molybdenum 3 remains stable for long, irrespective of whether it is 3D or it is 1D. So here, I'll again slightly change the direction. So what I mentioned so far, we used methylammonium as the cation, and then I briefly shown a replacement of methylammonium with cesium to tune the dimensionality from 1-dimensional to 3-dimensional. Now, what we can do, apart from these cases, one can change the cation to a very long cation, which here it is a double, the diammonium cation. And this will basically break the halide bonds along one of the axes because it's a linear cation. So you the remaining lattice will be a 2-dimensional lattice, which is corner connected in AB plane. And what we see in this molybdenum compound, where we have the diaminobutane in the interlayer gap, which is robust, the very strong stable lattice. But essentially here we see at the room temperature, we have methylammonium cations, which are or 2 different forms. One, we see there's a difference in the thermal parameters. And then when we heat this compound, one of the butane diammonium cation change from gauche to the all antiform. So there's a partial change in the conformation, and this is clear from the cavities that we have here, where the ammonium cation sits. We see selectively one of the cation become large at high temperature, and this leads to a phase transition around 160 degrees C, which is reversible. So this indicates that in such type of materials, one can put ammonium, diammonium, or even a single ammonium cation to look as phase transition under this material. So I'll briefly, for a minute or so, I'll talk about the earlier discovery that we did on ruthenium compounds, which are similar to these systems. And in the ruthenium compound, you can have as a double perovskite with ruthenium and silver, or ruthenium and copper in the 2D system. And then various cations can be used to pillar these 2D sheets at certain distance. And here the various compound which we could develop. You see there, band gaps is between 1.5 to EV, quite narrow band gap. And they're again very stable compound. And then we looked at their magnetic exchange interaction. So these are two types of system, as I mentioned. One is ruthenium-based, and the other one is molybdenum-based. And there's a difference in the number of unpaired spins. So here is the J-effective half system, and here it is actually, is a sequence system from SO sequence system, because L is 0, so it's only spin-only system. And this you can clearly be seen in the magnetic data analysis. We see the molybdenum system perfectly fits the Curie-Weiss equation, whereas the ruthenium-based system does not, because there's a spin-orbit coupling strength involved, and we see deviation. But however, this is still an open question where, we do not know why they don't fit and what should be the exact SOC value in the ruthenium-based system. More system need to be explored. Yeah, so with this, I'll conclude that while working on this system, we could develop various compound and can show how the transition metal can be incorporated in correlated system, which were the chemistry of transition metal earlier, particularly the heavy transition metal known as molecular system, but we can put in 2D and 3D and 1D system, and we can vary their dimensionality, and of course, we start to see some effect of spin orbit coupling strength in magnetism, but moving forward, more system need to be developed, and also we need to look at how SOC couples with the different. Okay, so with this, I'll acknowledge the people who contributed in the work. The work that we have been carrying out in Bangalore is mostly done by Devesh, the PhD student, and we collaborated with Thierry, with Professor Panpati. And most of the system, ruthenium, and that I've shown was done in my postdoc at UCSB in Tony and Ram's group. Thank you so much for introducing to the perovskite world and the funding agency. Yeah, thank you.
Thank you for a lovely talk, Pratap. Do we have any questions? Yeah, Didi.
Pratap, two short question comments. One with respect to the chlorine-bromine substitution, where you found that the bromine has a higher transition temperature. I would think that is to be expected because bromine will have a much stronger covalency. The hopping strength will be larger, and the J goes as T squared over U. So if T increases, the coupling strength should increase. So that's one thing.
Yes, thank you. Yeah.
And the other one, I was a little curious to know the 2.17 electron volt band gap that you saw in one of the cases. Are you sure that the one that you are taking the slope to determine the absorption edge is not the excitonic absorption? Because it looked like that you have a band absorption at a slightly higher energy, and this is an excitonic absorption.
Yeah, thank you. So we have in that, there's a small band before that here.
That would sort of clarify.
Yeah, so we measure along this one,
Yeah.
and this is a band which is known in the literature as a weak spin-forbidden ligand to metal transition. So,
okay, yeah, maybe I can talk to you later, but I think a temperature-dependent absorption study would help you to identify if that big feature is excitonic or not.
Thank you.
Tony. Yeah,
Thanks. Thank you, Pratap, for a really nice talk. Can you go to this? It was about this compound here, this double perovskite with molybdenum. Can you go to the structure of it? Yeah. So it hadn't occurred to me before, but these double perovskites are highly frustrated, and in principle because you get this tetrahedral arrangement.
Yeah.
And so, have you tried making the ruthenium analog of this? Because, of course, with the ruthenium, you'd have a much smaller magnetic moment, so you've got a much higher probability of getting a quantum spin liquid system.
Yeah, this is something we have plans to explore, but we have tried a few times. What happens is probably the more stable phase, that is the cesium-3 ruthenium 2 chloride or bromine 9 actually gets isolated. So again, yes, but it's a nice comment, a suggestion. So I think that phase need to be suppressed, and then it's possible to have a 3D phase. But looking at the geometrical parameters should be possible.
Yeah. Thank you.
Thank you very much.